Hey guys, this is going to be my video on 6.4 from our textbook, which talks about polynomial functions and their shapes, what we can expect from them, as well as end behavior expressed in something called limit notation, which is going to be huge moving forward into higher levels of math. And so we're going to be covering all that, giving you an intro into limits. And so here we go. We're going to start with a little bit of vocab. So some of this you'll already know. Polynomial in one variable. It's a polynomial, multiple terms. It only has one variable, pretty self-explanatory. And it also, for this definition, just says no negative exponents. We only have non-negative exponents, meaning we're never going to be dividing by exponents in these polynomials in one variable. So they'll look kind of like you're used to, 3x to the fourth plus 2x squared minus x plus 6. All positive exponents, no negative exponents. Leading coefficient, we've actually already defined back in 6.2. It's the coefficient, that number in front of the term with the highest degree. Examples below, but hopefully you kind of remember what that looks like. And then a polynomial function is just a polynomial equation that is used to represent a function. So just some of the common polynomials that we talk about, some of them we've already seen. A constant polynomial is a polynomial that just has a number, no x's. It's a constant value. So in this case, 9, the degree is 0 because there were no x's. Leading coefficient in this problem was 9 because that's the coefficient of the highest degree term. What about linear? Linear, we know it has that root word line. We studied that a lot in chapters 2 and 3. X minus 2. X minus 2, just x to the first, that is a linear polynomial. Degree is 1 if it's linear. And in this problem, the leading coefficient was 1 because it was like 1x to the first. Move on to quadratics. That was the subject and the focus of chapter 5. Quadratics have x squareds. So 3x squared plus 4x minus 5 is our example here. And so x squared means the degree is 2. And the leading coefficient on this problem was 3 because, well, it was 3x squared. So that x squared was the highest degree term, 3 there. And then finally, this one we're probably not as familiar with, but we will get very familiar with, a cubic. What is true about a cubic? Well, that means it has x cubed, x to the third. So degree is 3. Our example there was 4x cubed minus 6. So what is the leading coefficient? 4 in this case, because it's that number in front of the highest degree term, 4x cubed. So just a little bit of vocab there for you to get us going, get us started on this lesson. Now, one thing that is covered, but the good news is I think we should feel pretty good about this already, is evaluating polynomial functions. How do we do that? We're told g of x equals x squared minus 4, so we know g of 5, we'll plug a 5 in for x. G of 20, we'll plug a 20 in for x. But here we're asked, what is 2 times g of c plus 2? So 2 times g of c plus 2. How do we evaluate that? Well, all that's asking us to do is find g of c plus 2 and then multiply it by 2, double it. So I'm going to say 2 times c plus 2 squared minus 4. And so just like I was saying earlier, just like we've seen, we're plugging c plus 2 in anywhere we see an x. What is c plus 2 squared? Remember, c plus 2 squared means c plus 2 times itself, right? Times c plus 2. So I do need a FOIL, so that's c squared plus 2c plus 2c plus 4, c squared plus 4c plus 4. Okay, so that was just a little bit of side work. 2 times, I'll write that down, c squared plus 4c plus 4. And then don't forget, that was just the squared part. We also have this little minus 4 that we also have to take into account. I'm just looking at simplifying plus 4 minus 4. It looks like we could write this as just 2 times c squared plus 4c. So final answer is looking like 2c squared plus 8c. Just a lot of simplifying. We're plugging in c plus 2 into that g of x function. And then after we've done that and kind of worked it out, we multiply the whole thing by 2. Let's do another one. 3 times g of 2c. So we've got 3 times g of 2c. So what is g of 2c? Again, I'll plug in 2c there. 2c quantity squared minus 4. Now, the nice thing here is it's all one term, 2c, so I can just square it directly. There are no pluses or minuses. 2c squared would be 4c squared. 2 squared is 4, c squared is 4, minus 4. So now I can distribute the 3 because I've kind of worked out that inside. 12c squared minus 12. There we have it. Now, this last example is just to show you we could have some more complicated, if you will, looking functions, but it's all the exact same. 2 times g of c plus 2 plus 3 times g of 2c. And the nice thing is I worked these out just a second ago. Yeah, I did do that intentionally, but I know that 2 times g of c plus 2 is 2c squared plus 8c from 2 problems ago. And then 1 problem ago, we found that 3 times g of 2c is 12c squared minus 12. And so what does that kind of mean for us? Well, now it's just a 6.2 problem of simplifying this addition, these 2 polynomials being added together. Let's combine those like terms. 2c squared plus 12c squared is 14c squareds plus 8c plus a negative 12, so minus 12 looks like. And there we have it. So evaluating polynomial functions. Yes, it's covered in this chapter and in this section, but I think hopefully you have a pretty decent grasp on it already, and with these 3 examples, just kind of refreshing your memory, you'll feel pretty good on those. Which brings us to kind of the second half of the lesson. Now, usually I'm drawing all over the place with my hands, and I'm going to try to do that on the video, but I want to talk about how can we predict what a function's graph will look like? Because there definitely are ways. So I'm going to start here with this constant function. And the question I'm going to ask is, we've seen constant functions before. What do they look like? Just lines that are completely horizontal, right? They just go straight across. They are constantly the same value. Okay, so just going flat across, no ups or downs. What about a linear function? Linear, we've seen those, just a line. Maybe it's uphill, maybe it's downhill, who knows? But it looks something like that, right? And then I'll go to quadratics. Maybe it's an upside down parabola, maybe it's a right side up parabola, but we know what they look like in general. They look like a parabola. Now, before I get to this bottom row, I want you to notice something. The constant function, how many ups and downs does it have? The answer is 0. It just goes straight across flat. No ups and downs. So when it's degree 0, it has 0 ups or downs. Not a coincidence. This linear function I have drawn just goes uphill the whole time, right? It just goes up, 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 up. It just has 1 up or down. It's degree 1. Now a quadratic is degree 2. It has x squareds. And think about what this parabola shape is. It's going up and then it's going down. Up, down. It has 2 ups or downs, degree 2. Even if it were flipped, if it were right side up, it would go down and then up, right? So it would still have 2. And we're going to use this, what we just talked about, to now predict what will some of these cubic functions look like. So let me draw a sample cubic function. This is what some of them look like. They'll say 1, 2, 3. And you'll notice, again, I went down, up, down. 1, 2, 3, and because it was degree 3, it was x cubed. I can count on it looking something like that. There are different forms. Maybe it opens up, maybe it opens down, so to speak. but degree 3 is going to have 3 ups and downs. What about degree 4? 1, 2, 3, 4. Down, up, or maybe if it's flipped, up, down. It has 4 kind of up, down directions. And so degree 4, x to the 4th, we can count on it having that as part of it. One more, x to the 5th, because why not? 1, 2, 3, 4, 5. We'll say up, down, up. And so I'm hoping me doing this in the air in the video and also drawing it on the notes kind of makes a little bit of sense. We're going to be using that, especially next section, 6.5. Before we get there though, I want to talk about one more trend we see and also how we express end behavior with limit notation. This limit notation looks complicated, but this is something you're going to be seeing this year. You're going to be seeing it more in pre-calc. You're going to be seeing it a ton in calc. So as you kind of progress through these math classes, you're going to just be seeing more and more of it. So I'm going to try to give you a good intro and basis for it right now. Limit notation. Limits talk about what is happening to our graph at a certain point in the graph. And so they're written like this. And how that box on the right is pronounced, how it's kind of spoken is the limit as x approaches some value of f of x equals blank. And so let me just draw a quick example here. A very quick example. I'll go 1, 2, 3, 4, 5, 6. That would be like an x to the 6th, right? 1, 2, 3, 4, 5, 6. Who knows what it is, but I'm going to call it f of x. Okay. So if I wanted to talk about the end behavior on this graph, that means I am really interested in what is happening as this graph goes all the way to the left, towards the left negative end for x's, and all the way to the right. As we go all the way to the right, the positive end for x's. Now, each graph is going to have 2 limits when we're doing it this year. So I'm going to write them out. The limit as x approaches negative infinity of f of x. So I'm saying, I'm trying to describe what is happening to this graph as the x's are going more and more towards negative infinity. As we are going left and left, what is happening to our graph? Well, our graph is going up and up and up and up and up and up. What is it approaching? Well, the limit of f of x is positive infinity. As my x's are going to negative infinity, that's this part right here. The limit as x's go to negative infinity, as I go left, what is my graph doing? What are my y values doing? And that's that part right there. They're going to positive infinity. Let's do the other side of the graph. I mentioned each one of these has 2 ends. So for end behavior, we're going to say, what about as the x's are going towards positive infinity? So the limit as x approaches positive infinity of f of x, it's also going up forever, right? So would also equal positive infinity. The limit as x approaches positive infinity of f of x equals positive infinity. So we're going to get a little bit of practice writing these limits, analyzing graphs, and tie it back to kind of some trends that you will be seeing with our graphs. So I've got a little chart here, and you can pause it if you want. You can draw this out. You don't need too much room by each one. But you can see that I've got 2 rows, and the rows are labeled leading coefficient positive and leading coefficient negative. And then I've got 2 columns, even degreed functions and odd degreed functions. And so I'm going to kind of illustrate what we know about these trends for end behavior. Let's start right here in the top left. An even degreed function that has a positive leading coefficient. Let me write one here that we're really familiar with. Positive x squared, right? Even degree, positive leading coefficient. And we know kind of what that looks like. It looks something like this. Just a rough sketch, but looks something like that. So let's practice writing these limits. Two limits, one for the left-hand side, one for the right. So the limit as x is approaching negative infinity here of f of x. What is happening to my graph as I go left, left, left? I'm going up, 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 up. And so I'm going to say positive infinity. The limit as x approaches negative infinity of f of x is positive infinity. What about the right-hand side? What about the limit as my x's go positive? As my x's are approaching positive infinity, what is happening to my graph? It is also going up, up, up. So limit as x approaches positive infinity of f of x equals positive infinity because both sides are going up. So that one on the left says as my x's are growing negative, as x approaches negative infinity, my graph is going up. The one on the right says as my x's are approaching positive infinity, as I'm going right on my graph, I'm also going up. I'm going to drop it down here to negative leading coefficient. And so let's say we had like negative x to the fourth. Now this will just be a very rough sketch, proof of concept. Doesn't look exactly like this on your calculator, but 1, 2, 3, 4. Let's say something like that. Well, we can write limits for this. Limit as x approaches negative infinity of f of x. What is happening as I'm going left, left, left on my graph? It's going down, 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 further and further, right? So the limit that it is approaching is negative infinity. The limit as x approaches positive infinity on this graph of f of x, as we are going right, 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 we are also going down, down, down. So the limit of f of x is also negative infinity. So first thing to note here, we did the even degreed functions, and this is a good thing to jot down. I have it also at the bottom of these notes. Any even degreed function, the arrows point the same way. They both point up, they both point down, no matter what, for every even degreed function. If it has a positive leading coefficient, if it's positive x squareds, positive x to the fourths, positive x to the sixths, we're both pointing up. If it's a negative leading coefficient, we're both pointing down. So even degreed functions point the same way. And if it has a positive leading coefficient, they both point up. Negative, they both point down. What about odd? Odd, I'll go with f of x equals positive x cubed. Again, this isn't exactly what it'll look like in your calculator, but we know that positives, x cubed should have 3 kind of changes of direction. So 1, 2, 3, we'll say. What is the limit as x is approaching negative infinity of f of x? So as we go left, left, left on this graph, where is my graph going? Down, down, down. It's approaching negative infinity in the y direction. And on the right-hand side, the limit as x approaches positive infinity of my graph f of x, what's happening is I'm going right, right, right. X is approaching positive infinity. I'm going up, up, up. And we'll call it like that. How about a negative leading coefficient? So f of x equals negative x to the fifth, which will look something along the lines of 1, 2, 3, 4, 5, say. It's not a very pretty drawing, but that's okay. It'll look something like that. 1, 2, 3, 4, 5. Well, I could say that as the x's are going negative, as the x's are angling towards negative infinity, what is true? As x approaches negative infinity, f of x is actually going up in this case. So we'll say f of x, the limit is positive infinity. And over here, limit as x approaches positive infinity of f of x. Well, what's happening as my x's go positive? my y's go more and more negative. Now this is a trend as well. We had the trend with the even functions where they both pointed the same direction. Odd degree functions always point different directions on opposite sides of the graph. And how do we know which way they point? Well, if it's a positive leading coefficient, I'm going to argue, and this isn't strict like math terminology, but it kind of has a positive slope. We started low and overall we're ending high, an uphill slope. So that's how I remember, okay, that means it has a positive leading coefficient. It starts low, ends high. If it has a negative leading coefficient, it will always be starting high, ending low with kind of an overall negative slope, if you will. So again, I promised at the bottom, I would have just that quick footnote. If the degree of the function is even, the end behavior is the same towards positive and negative infinity. As we go positive and negative infinity, they both point up or they both point down. If the degree is odd, the end behavior is different. One points up, one points down. And if this weren't a video, if we were in class right now, I would be making you stand up and do this odd, odd, even, even dance, odd, odd, even, even. That looks silly and sounds silly, but actually like really helps people remember, including me. And it's funny, like during tests, you'll see people in their desk going, odd, odd. Okay, so this is an even one. But remember, odds point opposite directions, evens point in the same direction. Now, the limit notation is maybe the hardest part of this, because if I had just asked you, hey, what's happening as we go left here? You would have told me it goes up. I mean, it's not that complicated, but what is this saying? This is saying the limit as x approaches negative infinity, that means as we go left of our graph, f of x, is positive infinity, that means it goes up. Really practice and pay attention to, focus on writing these with proper limit notation. I think that's the hardest part, and if you can get that down, then it'll make life in future classes that much easier. So guys, this whole section was kind of just a, what do polynomial graphs look like, especially those higher ordered ones. Hopefully it made sense. If you have questions, write them down, bring them to me next time we meet, and we will talk then. But until then, take a look at your practice problems, practice that limit notation, evaluating functions, finding those leading coefficients, things like that. And I will see you next time.